and so please.
Okay, thank you very much. So first of all, with all due respect to our YouTube audience, as I mentioned to Boris earlier, we're here with Boris and Amir and Uzi, and I'd like to say hello, nice to meet you. It's a very intimate audience, so I would very much, actually, I don't know if you want to turn on your camera, Amir, just to say hi, you can turn it off. I'd love to meet you, and we can make this as a more of a intimate discussion as hello, thanks, as you wish. So definitely feel free to interrupt me. We all come from different backgrounds within mathematics. I don't have to go through my entire plan. Definitely we can make use of the fact that this is a small audience to actually make it more of a discussion and more interactive. Feel free to interrupt it anytime, just unmute your, oops, sorry, there we go. Just unmute your microphone and don't try to be very polite. This is a colloquium. The title of my talk is Classification Results in Equivariant Symplectic Geometry. So I definitely will need to tell you what I mean by classification, what I mean by equivariant, and what I mean by symplectic. And nevertheless, I would like to start with a fairly long digression on what might seem to be a very, very naive topic, which is polar coordinates. And there's reasons for this digression, because some of the questions about polar coordinates that I will present are, in some sense, baby versions of types of themes, challenges, and techniques that show up in the heavier projects that I'm sort of mentioning. So we know what polar coordinates are. We will work with R2. Now, I will identify R2 with the complex numbers. I will not actually do complex geometry here. At the very, very end, depending on time, I might mention something about complex structures, but here I'm using complex numbers just as a notational convenience. There's nothing complex in this story except maybe at the very, very, very end. So a point in R2, what does polar coordinates tell us? Polar coordinates tell us to describe a point in terms of its distance from the origin and its direction. So R here is a non-negative number, and U here is a unit vector, and I denote the set of unit vector by S1. And because I have identified R2 with C, I can write you in two alternative ways. I can write it as cosine theta sine theta, where theta is the coordinate modulo 2 pi. Or I can write it as e to the I theta, and I will go back and forth between these two. And then the polar coordinate map is simply the map taking the pair R. I'm sorry, I want to do it the other way around to be consistent. I want to take the pair U comma R to the vector R dot U, and geometrically speaking, so this is a map from the Cartesian product of the circle with the ray of non-negative numbers to the plane. And we know what, the Cartesian product is just a half cylinder. So it's a special case of a manifold, two-dimensional manifold with boundary. And here are the circle directions, and you can see the ray direction. And the map to the plane, we know it works beautifully away from the origin, but of course at the origin, there's a whole circle getting collapsed to a point, which create some awkwardness. So for a lot of purposes, if you want to use polar coordinates, you're going to be in trouble if you're near the origin. One of the things that we see from this polar coordinate, actually, let me actually draw the images of these circles as concentric circles on the plane. And here, the way that I drew it, the points in the half cylinder, I drew the circles that are equidistant, and then the radii are equidistant in the plane. But this map, of course, does not, it distorts area. Now, measurement of area is the first version of symplectic geometry. Symplectic geometry works in high dimensions, but it is about two-dimensional area, and in two-dimensional manifolds, this is just measurement of area. So for example, if I take like two little shapes here of the same area, different by a let me actually draw the image here. I'm going to try to draw the image of this shape. Here we go. Something like that. I'm going to draw another shape Oh no. Okay. I thought I charged my Apple Pencil and it's complaining about low battery. If there's any, maybe oh boy. Okay, sorry. The charger was not plugged in. That's going to be pretty bad, but we're going to, hopefully it's going to be okay. I might need to interrupt for a minute if it goes really bad. So let me try to draw the picture. Here's another one. And I tried to draw them sort of the same areas, but of course, in the image here, we're not seeing the same areas. And of course, in terms of formulas, again, for those of us who are fluent with differential form notation, the lack of preservation of area reflects the fact that the area form in the half cylinder does not go to the area form on the plane. But we know how to fix this, of course. Got the usual formula. And let me write the usual formula in terms of a new coordinate, which is r squared over 2. And when you work with s, namely r squared over 2, instead of the radius, this is what we call symplectic polar coordinates. And the word symplectic indicates the fact that as soon as you place r with s, the picture will be very, very, very similar, but we will no longer have distortion of area. We'll have distortion of shape, but not distortion of area. And let me for a moment just omit the factor 2. The factor 2 is not very meaningful for the purposes that I actually care about. So let me now write symplectic polar coordinates. And let me write this symplectic polar coordinate map as, hold on, as us going now to square root of s times u. So, and same picture as before. I'm going to try to fit it in here. But now the radii are not quite equidistant, but there's this equi-area. So this does preserve area. So this is a symplectic transformation, symplectic version of polar coordinates. Now, I said I don't do complex geometry. Well, I mean, sometimes I do, but most of what I do, in particular the stuff I'm talking about today, has to do with C infinity geometry. So everything here is going to be, we will care about maps that are infinitely many times continuously differentiable. And now comes the question on how, can we use polar coordinates how do we do differentiability in polar coordinates? Or let me write here the question as smooth functions in polar coordinates. And of course, you're going to be in trouble here, but there's some interesting features to this trouble. So here I'm giving away the answer. This is not going to work very well. And it will not work well whether I use the ordinary polar coordinates or the symplectic polar coordinates. That's not going to make much of a difference. So let me, in this case, use the ordinary polar coordinates and compare a smooth function. I'm sorry, compare a function, real valued function on the plane to a real valued function on the half cylinder. Of course, to be able to compare the function of the half cylinder, better be constant on boundary. So they are related, of course, by, oops, U R equals H of RU. And well, as sets, there's not, set theoretically, there's no problem. We got a bijection between set maps. And it is a, fairly straightforward exercise in points of topology to show that continuous maps correspond to continuous maps. And of course, the polar coordinate map itself is smooth. So if you have a smooth map on the plane, smooth function on the plane, it goes to a smooth function on the half cylinder. This is not going to work for the symplectic polar coordinates, but the opposite direction works for neither of them. So as far as smoothness is concerned, we don't have a good correspondence here. And it's kind of cute to see, like, okay, so what is the criterion for the polar coordinates? And how can you tell that the function is smooth by looking at the polar coordinates? That's kind of a, food for thought. And now when you do smooth geometry, so you care about real value functions, you also care about diffeomorphisms. Diffeomorphism is just homeomorphisms. Well, I would say bijections such that they and their inverse is smooth. So let me ask similar questions. And again, this will be disappointing, but again, there's a pretty interesting aspect there that I will mention. So the upshot will be, okay, these are not so good, but there's something interesting happening here. So let me again look at the polar coordinate map. And downstairs, I will take a diffeomorphism, and to have any chance of lifting it upstairs, we're going to take a diffeomorphism that takes the origin to itself. And upstairs, I will take just a diffeomorphism, and automatically it has to send the boundary to itself. And I'm going to ask, like, if I have a phi, does it lift to a psi? If I have a psi, does it lift? If I have a psi, does it the descent? Does it come from a phi? And well, diffeomorphism upstairs will descend to a homeomorphism, but not to a diffeomorphism downstairs. The direction from down to up does work, and that's actually pretty interesting direction. So although the upshot is like, okay, we're going to be disappointed here, one of the two directions does not work. But there's something interesting going on, which involves sort of interesting ingredients here. Going from diffeomorphisms. Oh, I'm sorry, I said something else. I said something incorrectly about homeomorphisms. So let me pause for a minute and talk about homeomorphisms. If you want to do homeomorphism, you're going to have exactly the other way around. If you have a homeomorphism upstairs, it will have to take the boundary to the boundary, and it will descend to a homeomorphism of R2. So for homeomorphisms, going from up to down is good. For homeomorphism, going from down to up might not be good, because, for example, you could take each circle up center at the origin to itself, but the rotation, you can rotate these circles by angles that don't converge to anything as you approach the boundary, and that will give you homeomorphism of R2. In fact, even equivariant with respect to the circle action, that does not lift, where the rotations of the circles might not have a limit as you reach the boundary, and then upstairs you will not know where to take the boundary. So for homeomorphisms, even equivariant homeomorphisms, going from down to up will not work. Going from up to down will work. So we have sort of a very different behavior from diffeomorphisms versus homeomorphisms. Let me say a word about why going from the down to the up does work. This is a special case of something that is called radial blowup. Basically, this is a procedure, in this case, taking the origin in R2 and replacing it by the circle, but doing it in a way that sort of keeps tracks of a smooth structure. And radial blowup is a procedure that is well defined in higher dimensions as well. If you have a manifold and a submanifold, there's a well-defined procedure of so-called radial blowup along the submanifold, where you place the submanifold by the circle bundle of its normal bundle, sphere bundle, sorry, by the sphere bundle of its normal bundle. And there's a way to put a manifold structure, manifold with boundary structure on the resulting space that is independent of choices. Independence of choices has to do exactly with this feature that diffeomorphisms downstairs lift to diffeomorphisms upstairs. And the proof of that uses my favorite lemma in calculus, absolutely favorite, which is called Hadamard's lemma. And let me give you the statement of Hadamard's lemma that we're using here. In some sense, Hadamard's lemma can be thought of as some version of Taylor theorem with remainder, but not quite, because this is a theorem, this is a lemma that's very, very useful when you want to do sort of smooth geometry. So this version of Hadamard's lemma says you take a smooth function on the plane. Smooth means infinitely, continuously differentiable to all orders. And suppose it takes the origin to itself. Then the lemma tells you that you can actually express it in the following way. There will exist a smooth map from that associates to each point in the plane a 2x2 matrix, such that our smooth map phi at each point is obtained by taking that matrix and acting on the point. Now here I'm using complex notation, but this is everything here is real. Z here is just a 2x1 vector. A here is a 2x2 matrix. Do I have questions so far? Or comments? Beautiful lemma, beautiful lemma. Well, in fact, in this case, this is just linear approximation, except that the remainder is hidden into the fact that the matrix is not constant. It's a smooth function. Now, the tricky thing about this lemma is this map from R2 to R, the map that satisfies this condition from R2 to matrices is not unique. You can even choose such maps that are not even continuous. But the point is you can choose, the proof is not hard, but you can choose the map to be smooth, and that's really powerful.
A question, how unique is this A?
It's very non-unique. So there is a way of choosing it. There's a natural way of choosing it by sort of looking at, well, I mean, I can give you the proof. It's going to take another like 3 minutes as a consequence of fundamental theorem of calculus integrating along. So there's a canonical way of doing it, but it's not unique. It's not unique. So I could have a recipe of constructing one of these, and that recipe will be beautiful and smooth as a function of parameters if everything was depending on a parameter. But if I just tell you the property of A, very non-unique. Doesn't have to be continuous. And that's what makes it kind of charming, the fact that you can do it smoothly. You want to see a proof? It's easy. It's easy, but it's really useful, really powerful. Well, you know what? No, let's leave that to the. Okay, let's move on. Everything is nice and beautiful when I want, when I care about, when I take into account the circle action. Circle acting on the half cylinders just by rotation of the S1 coordinate. Circle action, the plane is by rotations. And any of us who sort of taught calculus or took some basic physics, we know that polar coordinates are useful when you have circle symmetries, just like spherical coordinates are useful when you have three-dimensional rotational symmetries. So doesn't come as a big surprise that once you allow symmetries, everything's going to be nice and happy. So suppose I take S1 invariant smooth functions. And now it actually starts to make a difference. Here, I really want to use symplectic polar coordinates. They're going to be, so I care about not the symplecticness, I care about smoothness, but in this particular situation, the symplectic polar coordinates will do the job, will sort of be nice for smooth aspects of this story. So here I can already tell you, everything's going to be nice and happy. And let's draw the diagram. Here is my symplectic polar coordinate map. And let me again look at real-valued smooth functions. Oh, real-valued functions, I'm sorry. And when I look at circle invariant functions, upstairs, I don't have to worry about it being constant on the boundary. That will automatically be true. And at this point, we have a bijection. And the main ingredient here is a theorem of Whitney from the 1940s. By which, if you have on the real line a smooth function that is even, f of x equals f of negative s, then you can write it as a smooth function of x squared. And on the level of polynomials or power series, this is trivial. So the content of Whitney's theorem, an even function of x is a smooth function of x, is a smooth function of x squared. The content of that theorem really is in the sort of the depth here is lying in the distinction between smooth and analytic, because dealing with flat functions is a piece that actually requires some care. And easy consequence of Whitney's theorem is if you have an invariant smooth function on the plane, then you can write it as a smooth function in radius square. And this is the reason for this nice correspondence between smooth functions in symplectic polar coordinates. And we also have a beautiful and nice correspondence when you do, when you do S1 equivariant diffeomorphisms. In symplectic polar coordinates. And let me write this. Once again, we have the symplectic polar coordinate map. Sorry, typo. I forgot to say something. I do tend to make a lot of typos. So if you're sort of following me or half following me, and there's something that looks a little bit strange, I do tend to make typos. So definitely stop me, because it might be a typo. So equivariant means a map that intertwines the circle action in the domain with the circle action, the type target. And again, you have this beautiful correspondence here. And this here, we definitely use Whitney's theorem. And there's one more. So we need Whitney's theorem, and we need Hadamard's lemma as well. So both of these are playing. Both of them are ingredients. This really fails for homeomorphisms. The same reason I mentioned earlier, if you have a homeomorphism downstairs, its lift upstairs away from the boundary might not extend continuously to the boundary. So this is the end of my very long digression about polar coordinates. Do we have questions at this point?
Yes, could you repeat the S1 equivariant condition, please?
Of course, of course.
What does it mean?
And this is really important, because I mentioned to you the title of my talk has the word equivariant. So what we have here, we have an action of the circle group. So on the half cylinder, this is a circle across the ray. This is just action by rotations on the circle component. And in the plane, this is just rotations about the origin. So this is an action of the circle group on each of these sets. In fact, manifold in the case of the plane and manifold boundary in the case of the half cylinder. And equivariant means this is a map that intertwines the two actions. If you first rotate and then take the map, that's the same thing as first taking the map and then rotating. So of course, this is an enormous limitation of the map. And this is sort of really a baby version of sort of much sort of higher stuff. But nevertheless, this baby version is interesting. So one consequence is that each circle has to go to a circle, but possibly not of the same radius and possibly rotated. And then the change of radiance and the amount of rotation, there's some condition on them for the function to actually be, suppose I'm starting with the downstairs, for the function to be smooth on R2.
Thanks.
Okay, thank you for the question. Yeah.
Or this work for higher dimensions as well?
So I deliberately gave I'm not going to answer this question, but I'm going to make a comment about it. This is very, very much I mean, I can give you some concrete cases where something similar works. To start, in this situation, you can definitely add parameters, and that's kind of a stupid thing to do. But if all your maps depend, if you start with a diffeomorphism, with a family of diffeomorphisms that depends smoothly on parameters, that this whole correspondence will still work, and the dependence will still be smooth as a function of the parameter. So this is a cheap answer. The true answer is, I've chosen here a sort of an analogy. This is not exactly what happens in our project, but I'm sort of hoping at the end of the talk to mention something about a classification project with Susan Tolman, which has been going on for many years. Part of it has been finished since a few years ago, but there's sort of a last part, which is not yet finished, still ongoing. But the part that is finished is already complete, which is, one of the features of our work is we work in a situation that is equivariant symplectic. We've got torus sections and symplectic manifold. A torus is just a group which is isomorphic to a product of the circle group with itself some finite number of times. And there's some assumptions there, and we're trying to obtain some classification. Now, the very first step we do is there's enough symmetry in that situation that using a method called Moser's method allows us to go from equivariant symplectic geometry to equivariant differential geometry. And then it turns out that the vast, vast, vast majority of our work and the big, big challenges are actually on the level of equivariant, I would say equivariant differential topology rather than equivariant. And the biggest challenges are we have an open dense set where everything is nice and beautiful and smooth, and we've got those singular pieces where your smooth structure breaks up, and that requires a lot of care and attention. So in this sense, the question I'm asking here is an analog of the type of questions that we have to work with in these higher dimensions. So it's an analog rather than, okay, a direct generalization, in that everything is nice and beautiful in this baby case away from the origin of R2, but then there's special care and attention that is needed at the origin. So that's, in that sense, this is an analogy of this sort of bigger project. Analogy rather than that it, yeah, okay. I'm not sure if this answers the question, but yeah. So let's actually go, actually, are there more questions about this sort of baby story? I kind of like this baby story, you can probably tell. Okay. So let's move on and let's go back. Like, what was the title? Classification results. So we know what the word equivariant means. It has to do with intertwining group actions, maybe circles, maybe tori. And we know that symplectic has to do with measurement of areas. And yes, I will focus on torus actions here. There's a lot to say, including my own project on groups that are non-abelian, but let me sort of focus on torus actions. So a torus is just basically just a product of circles. It's a Lie group that is isomorphic to a product of circle groups. So it's a manifold together with a group. And my M here is a symplectic manifold. Now, of course, a circle action on a manifold is just a periodic flow where the period is 2 pi. If you take circle group cross the circle group, this is just 2 periodic flows that commute with each other. And the same for torus. The torus action is just a collection of periodic flows, finite collection that commute with each other. And for a symplectic structure, the dimension will have to be even in order for the manifold to admit a symplectic form. Symplectic structure is a symplectic form. And if you're fluent with the language of differential forms, this is a differential 2 form that has 2 properties. It is non-degenerate, and it is closed. So the exterior derivative, which is a 3 form, has to vanish. And differential 2 form, what does it mean? At each point in your manifold, because this is a smooth manifold, we have a tangent space at each point, which is a linear vector space. So differential 2 form is just an anti-symmetric bilinear form at each point of the manifold. And non-degenerate is the usual definition for bilinear forms. At each point, we need it to be non-degenerate. Every non-zero vector has a friend. And this combination of non-degeneracy and closedness allows us to be able to choose very nice coordinates where you can actually write a very concrete formula. And this is the first example of a classification. This goes back to Darboux from, in fact, it's not quite in this language, but it goes back to the late 19th century. There exists, not in this language, of course, there exists local, but the content was there. Today, the proof is much easier. There exists local coordinates near each point. Let me write them as x1, y1 through x and yn, such that in these coordinates, omega is written with, well, constant coefficients, and moreover, just dx1 wedge dy1 plus dx2 wedge dy2, etc. And again, this is a very cute example. Let me do sort of a 2-dimensional example. Let me take the 2-dimensional sphere with a standard area form, where the integration of that area form over each region just gives you the area of that region. So here's a 2-dimensional sphere. And then you can ask, well, how do we write this in coordinates? It turns out that if you use cylindrical coordinates, then you bring it to exactly that nice Darboux form. So in this special case, cylindrical coordinates are a special case of Darboux coordinates. So let me write this down. So what are cylindrical coordinates? So I'm going to place the sphere inside the cylinder. Cylindrical coordinates are just take Cartesian coordinates, x1, x2, x3. x3 is left untouched, but we're taking polar coordinates in the x1, x2 directions. So these are cylindrical coordinates. And in cylindrical coordinates,
maybe you mean theta x3. Oh, yeah. Is r a coordinate?
So r would be, so the cylindrical coordinates would be r, theta, and x3, but this is, I'm sorry, these are cylindrical coordinates on, hold on, let me sort of fix this. This is on R3. Not on let me write this on R3. On the sphere, you would need 2 of them. On R3, you need 3 of them. And then on the sphere, you only take theta and x3, and that is enough to determine a point on the sphere. Of course, there's ambiguity at the North Pole and the South Pole. And taking cylindrical coordinates on the sphere means you're projecting the sphere, you're sort of ignoring the radius, the horizontal radius, you're projecting the sphere horizontally to the cylinder, and then you're taking the coordinates on the cylinder. That's defined outside the North and South Pole. So these are the cylindrical coordinates on the sphere. And in the cylindrical coordinates, the area form just becomes d theta dx3. So what that means is that this projection map from the sphere to the cylinder will preserve area. So for example, near the, if you take like a sort of a strip given by just a, you know, all this points on this two sphere between two very nearby heights, values of x3, around the equator, the strip will be fairly long but sort of thin. If you take such a strip near the North Pole, it's much shorter, but it's because of the slant, it's going to be wider, and these two features exactly cancel out. So you get, so if you take if you put the sphere into a bread slicer and you look at what happens to the crust, different pieces of the crust will all have the same area. And in some sense, this is actually goes back, again, of course, not in this language, goes back to Archimedes. Again, one of my favorite theorems in geometry. And so that this tells us that cylindrical coordinates are a special case of Darboux coordinates. So now let's do I have questions here? Should I move on? Okay, let's do something, you know, maybe a tiny bit fancier. I'm a little bit, yeah, okay, let's do something a little bit fancier here. Let's go back from Archimedes to the 1960s. Now, again, let's sort of still stay with 2 dimensions. Suppose we have a surface, let me call it sigma, with an area form. So some measurement of area, some smooth measurements of area and orientation. Definitely, if you have 2 of these, if you can find a diffeomorphism that takes the area form to the area form, this is an area preserving and orientation preserving diffeomorphism, it will have to preserve the genus. Having an area form means the surface has to be oriented. So, and then there's a total area. So definitely, if you have 2 of these, same genus and total area. And Moser told us the other way around. Moser told us a way that if you have the same total area, well, of course, if it's the same genus, you can find a diffeomorphism, but then you're going to have 2 areas forms with the same total area, but they might be different as area forms. One might be concentrated more on one side, the other on the other side. And Moser tells us, well, take the convex combinations of these guys to get a whole deformation of the area form, and he finds a way of writing an ODE that whose solution will be pushing your points around, so that's so as to sort of gradually move the first area form to the second area form. And this is a very, very powerful technique as realized by Alan Weinstein back in the probably 1970s. You could use it to prove Darboux's theorem. You could prove a lot of things. And let me now present the objects on which I'm actually talking about here in the special case of torus actions. The objects that I'm going to be talking about, their classification so here we have a little bit more structure. We have a symplectic manifold, and we have a torus action, and we have something that is called a momentum map. The target space for the momentum map is a vector space. So for example, if the torus is equal to S1 to the K, what happens in this case, then again, if you're familiar with the Lie language, then the Lie algebra of the torus is just RK, and we have the so-called exponential map from the Lie algebra to the torus itself, where this is basically just a quotient from RK to RK mod ZK. This being a like, okay. And then we have the dual of the Lie algebra. Well, you know, this too is RK, but not canonically. You need to actually, well, in this case it is because T was equal to S1 to the K. If we didn't choose a splitting of S1 to the K, this would not be canonical, but still, this is a vector space. And we connect the moment map is a way of sort of encoding the torus action through something called Hamilton's equations. This is really, when you write them in coordinates, this is the same as Hamilton's equations from classical mechanics. In the whole field here really came from classical mechanics, where symplectic manifolds are there to encode to model phase spaces in classical mechanics. And Hamilton's equation tells you the following: for each element of the Lie algebra of your torus, each one of these guys gives you a one parameter subgroup of the torus. And when you compose that with the action of the torus on the manifold, what you get a flow of on the manifold. And then you can take the generator of the flow, and that's a vector field on the manifold. At each point, like, what is the velocity of the flow? That's a vector field. And Hamilton's equation, if you haven't seen it before, it's not very intuitive, but what you can take, so this is, you plug in the flow in the two form, you get a one form, and that will be the exterior derivative of the xth coordinate of the momentum map. So it's fairly technical, but the thing to take from it is, actually, is that the torus action determines the momentum map up to translation, and the momentum map determines the torus action. So they're really, it's almost like this, they're encoding the same thing. And then and a lot of examples that we actually care about in nature do admit momentum maps, and then these are the objects, hold on, that we will be studying. We call them Hamiltonian T-manifolds, and this is basically the triple manifold symplectic structural momentum map. Momentum map encodes the torus action, and we will try to classify them up to isomorphism. Isomorphism simply means a diffeomorphism that preserves all the structure. In fact, T-equivariant we will get for free. But let me still spell it out. And I'm sorry, there we go. There we go. So it looks a little bit technical, but basically symplectic manifolds with a lot of symmetry. And the point is, one of the sort of features of this game is you can trade symmetry for dimension. When you have like higher dimensions but lots of symmetry, you have more tools to deal with this that are similar to what you had in low dimension, as is Moses' method, as is Moses' theorem that I mentioned earlier. Let me give you the first example of these guys. In some sense, this example is like almost like a building block of all of them, using some equivariant version of Darboux theorem.
Just to make sure, the torus action preserves the symplectic structure, right?
Yes, yes. But this is a fantastic question because you cannot see this from the definition. Oh, I'm sorry. You can preserve the symplectic structure. Yes, oh, no, hold on. Sorry. Yes, I'm sorry. So
talking about the group action.
Yeah, absolutely. Let me go back. So this can be a little bit subtle here. In this definition of momentum map, in my definition of momentum map, I did assume that the torus action preserves the symplectic form. But in fact, I could have concluded this as a theorem rather than assume this. So this assumption was in fact redundant. In fact, this technical condition for the momentum map does imply that the flows generated by the vector field psi m, therefore the torus action, do preserve the symplectic structure. So I did assume it, but I did not have to assume it. This is a theorem, which is, when you write it down, the proof is like really, really easy, once you're fluent with symplectic forms, but it's not obvious if you just look at the equation. So thank you for the question. Do we have more questions here?
Yes, yeah, can you scroll up again? And one more slide. I'm a bit confused. You mentioned something like total area as an invariant. There is some sort of normalization or something.
Oh, what do I mean by invariant? When I say invariant, what I mean is I refer to this direction. So when I say invariant, what I mean is if you have two surfaces with area forms, if you have a symplectomorphism between them, which means the same thing as a diffeomorphism that preserves the area form. So it preserves area and preserves preserve orientation. Then, of course, the total area has to be the same. So the fact that the total area is invariant is a trivial fact. It just means that if you have a isomorphism, then you have the same area. It's sort of, because what does it mean to be area preserving? It means like each region goes to a region of the same area, or like if the pullback of the area form is the area form. But then of course you can just apply that to the whole two manifold. So this is invariant under symplectomorphism. The word invariant refers to the equivalence relation, which is symplectomorphism.
Yes. Okay.
Yeah.
Thank you.
And then the hard part is to show that this. So the hard part is to show that this is a complete set of invariants. That's the other direction. So this piece says, let me actually add it to the notes here. This says, this is a complete. And that's the hard part. Okay? So, and that's a quantitative Moser's theorem. Let me move on. I'm a little bit behind with time, so I'm going to need to make some choices here. But let me sort of say something. So let me do the example. This is, again, it's pretty, once you write it down, it's sort of an exercise. Let's take the standard symplectic form here. And then we have the torus acting by rotations of each of the coordinates. And then the momentum map takes values in R to the n, which is, n is just a dimension of the torus here. And the formula for the momentum map is up to plus minus, just take the norm squared of the coordinates. So in fact, we see here that the up to factor of 2 possible plus minus sign depending on conventions, the symplectic polar coordinates of the different coordinates here, the radius square part of it is just an example of a momentum map for a circle action. And let me say a word. So the other word in my title was classification. And let me say a word about classification. It's sort of fairly general, kind of almost like philosophical. When you do classification, there's a few things you need to do. You need to give a family of invariants. So in the case of Moser's theorem, there was no symmetry. There was just a symplectic surface, and the invariants were total area and genus. Then we need to show that the invariants distinguish spaces. So we need to show that we had enough invariants to actually, and this is what we call uniqueness. But this is only half of classification. The other half is what we call existence, is say which values the invariants can take. So construct, for example, construct spaces from invariants. And the value, as soon as you have a classification theorem, the value of the two pieces are a little bit different. So let me say this verbally, not write it down. When you have the complete set of invariants, this is good for proving theorems. And in this particular case, different versions of classifications have, sometimes you care about symplectic manifolds and you don't, they have a lot of symmetries, but you don't care. Sometimes you're interested in like symplectic invariants that do not care, that completely don't care about the symmetries. But sometimes the combination of lots of symmetries together with this uniqueness part of classification, which is enabled by the presence of many symmetries, sometimes that helps you give information about the manifold that was purely symplectic information about the underlying symplectic manifold, and that even if that information was not had nothing to do with the symmetry. Specifically, if anyone is familiar with this language, or in symplectic geometry, there's like a hard symplectic invariant, so-called, which is called Gromov width, having to do with how big of a symplectic ball can you embed in a symplectic manifold. And in a sequence of papers in recent years by a bunch of people, many of whom were my students and postdocs, there was like almost and very, very close to being a complete verification of a conjectural formula for the Gromov width of so-called coadjoint orbits. Coadjoint orbits is a fantastic collection of symplectic manifolds built from Lie theoretic data, including Grassmannians of all types, and generalized Grassmannians and flag manifolds, etc. And we have a conjectural formula for the Gromov width, which is symplectic invariant of this guy, has nothing to do with the symmetries, but you can use various kinds of symmetries to confirm this conjecture. And by now it has been confirmed in almost all cases. So this is an example for how uniqueness features can actually help you prove theorems. Existence is wonderful because it allows you to construct a playground. As soon as you have a way of constructing lots of examples, you can start playing with them. So that has been the value of existence parts of classification. Now, I think my time is almost up, and I have to decide what to talk about. Let me say another something verbally. Let me stick with the case of torus actions, and let me define the complexity, which is one of the words that appeared in my abstract. And this is how far is the torus from being half the dimension of the manifold. In the example I gave you for rotations of the coordinate of Cn, the torus was half the real dimension of the manifold. And that's the biggest symmetry you can have if you have a momentum map. In the other example, Moser's theorem, there was no symmetry, 0-dimensional torus action, and the manifold was 2-dimensional. So in that case, the complexity was 1. The complexity will always be non-negative. And if I had some extra time, I would give you a statement, but let me just tell you about the statement of the classification, which the 3 papers that are already out give you part of it. There's a 4th that gives you the rest of it. And this is the classification of complexity 1, Hamiltonian torus actions. There's some technical assumption here. You need the momentum map to be proper, which is proper. Pre-images compact sets uncompact. And the piece that is published is under the an additional assumption, which gives you a big playground. And that assumption means, well, the level sets of the momentum map turn out to be invariant under torus action. Their quotient can be either single points. Their non-empty quotients can be either single points or 2-dimensional. And this is so at least now I'm being honest to you. What are the assumptions of the published part of this classification. That does give you fantastic big playground, lots of examples there. In some sense, many more examples than the remaining part. I'll stop here, and thank you very much. And I'm happy to take any more questions that you might have.
Thanks a lot. So are there any questions or comments? So you say classification, is it difficult to state at least approximately what?
Yeah, I was planning to state it. I gave a similar talk not that long ago where I was actually able to give the statement. Mm-hmm. Obviously, when you do classification, you want to state it in terms of simpler objects. Mm-hmm. The piece that is an earlier piece of work from the late 1980s is when you have complexity 0. That's work of Delzant. Mm-hmm. The image of the, let me do like 2 more minutes.
Sure.
Here's a momentum map. Any dimensions whatsoever, the image of the momentum map is a convex polytope. Suppose that this is compact. Let me make this a simplifying assumption. You can do versions which are not compact, but is a convex polytope. So, Delzant tells you complexity 0. In complexity 0, these spaces, modulo isomorphisms, are in bijection through the momentum map with convex, let me do dimension n, so-called unimodular polytopes. So this is sort of a model from the late 1980s, beautiful theorem of Delzant. Complexity 1, obviously, you would, as you expect, the classification is a little bit more difficult. Let me do the tall case.
In RK. In RK, no?
Actually, complexity 0 is exactly the situation.
Okay.
Yeah, here we go. Yeah, no, this is fantastic comment. This is exactly the situation where K is equal to M. So a priori, just to have a polytope, you don't need any dimension assumptions. But complexity 0 is when K is equal to M. 1, K is equal to N minus 1. So, I mean, that requires a little bit more. Let's say take the geometric quotient. Here's the momentum polytope, the momentum image. The momentum map descends to a map from the quotient to the image. And this guy is homeomorphic. This is actually kind of up to topologically speaking, you've got just a polytope across the surface. Smoothly, this is interesting. On an open-dense set, this is nice and smooth, but on some interesting stuff, you're going to have some failure of the smooth structure, which you have to be more careful about. Now, from the torus section, you can decompose, you have a sort of finite decomposition of the manifold into so-called orbit-type strata. You take all the points with the same stabilizer and take the connected components of that set. These are the strata. And then there's a skeleton. Now, the strata themselves are themselves sort of little smaller Hamiltonian T-spaces sitting inside the bigger one. And some of them will have complexity 1 and some of them will have be toric. So you've got this high dimensional manifold, but all these Delzant spaces sitting inside it, which are, the complement is open and dense, but these are the interesting ones. So what you have in that situation, this is just, you know, closure of each of these guys, its closure is just identified with a convex polytope. So you have a whole bunch of convex polytope glued sort of, along their faces. And the classification is in terms of this guy. So what are the invariants? Well, you need the skeleton. So this is this collection of convex polytopes glues along their faces. And you need a little bit of data here. Each of these guys, you need to remember where it came from. What was the stabilizer of the points on the manifold that gave rise to this stratum? And how did that stabilizer act? What was the linearized action of the stabilizer on the tangent space, the linearized isotropy sort of, or if you some, let's say, plus labels. So let me write this as labels. And then you have the inclusion map, and you just need this up to homotopy inclusion. So theoretically, there's inclusion, but you need to sort of see how does it sit, and that can be super interesting because you can have some interesting topology for this inclusion. You're never going to see that if this came from a Kähler manifold. You're never going to see that. So there's really very interesting topological aspects here that you don't see in the presence of a complex structure. There's something called a Dussmann-Teckelmann measure, but this is just encoded here based on parameter. And that's it. So this is just roughly, these are the classifying invariants.
Thank you. Any other questions? Okay, if not, thanks a lot again.
Okay.